Welcome to Unit 1, Lesson 5, Part 1, where we're going to explore some examples using the sum and difference formulas that we derived in a previous class period. So we derived these formulas. Why are they helpful? When we want to find an exact value, the only exact values that you can find at this point are angles that are either on the quadrants or quadrantal angles that are on the axes of your unit circle, or any angle that is formed by a 30, 60, 90 triangle, a 45, 45, 90 triangle, or it's an angle when we have reflected those triangles in the other quadrants. So what I have outlined for you here are all the angles that we can get an exact value. So if I wanted you to find the exact value of the sine of 75 degrees, 75 degrees is going to be located here on the unit circle. And that's not a place that was formed by a 45, 45, 90 triangle or a 30, 60, 90 triangle. So up until now, the only thing you could really do with the sine of 75 degrees is type it in your calculator, which would generate a decimal approximation. But if we want to find the exact value, I can use any of the angles you see highlighted in yellow and add them or subtract them to get new angles, and I can use their exact values to find exact values of new angles. So when I look at the sine of 75 degrees, I think to myself, what are some ways that I could use the angles that you see pictured on my unit circle to either add to 75 or subtract to 75? Well, one option, and I always go for the one that's the most efficient and easy, is I could take two first quadrant angles, 30 and 45 degrees, and that would equal 75 degrees. But I could also get a little creative. I could take 120 minus 45 to get 75. I could also do 210 minus 135 to get 75. Any of these will work. It will yield the same results. First quadrant angles tend to be angles that you probably know the sine, the cosine, and the tangents maybe a little bit quicker. So that's why I would encourage you to use first quadrant angles when you can, but that's not always going to be useful. So sum and difference formulas are useful because if I wanted to find the sine of 75 degrees, I could break 75 degrees down into the sum of 30 and 45 degrees. Now, this is not the distributive property. I don't just distribute the sine to do the sine of 30 plus the sine of 45 degrees. I have to apply the sum and difference formula. So I say to myself, if I'm doing a sum and difference of sine, I would do sine, cosine, cosine, sine. All right, so I would write down sine, cosine, cosine, sine. Then the angles alternate. 30, 45, 30, 45. If you had written 45 plus 30, that absolutely works, and then you would have written sine of 45, cosine 30, cosine 45, sine 30. Because it is a sine formula, that means the sine, S-I-G-N, sine stays the same. So I'm going to take the sine of 30 cosine 45, which is a product, and add the other product of cosine 30 sine of 45. Next, I'm going to evaluate each of those trig functions. So the sine of 30 degrees is a half. The sine of 45 degrees is root 2 over 2. I'm going to add the cosine of 30, which is root 3 over 2, times the sine of 45, which is the root 2 over 2. Remember your please excuse your dear Aunt Sally rules. I need to do my multiplication before my division. So when I take 1/2 times root 2 over 2, I get root 2 over 4. When I take root 3 over 2 times root 2 over 2, I get root 6 over 4. And because those are common denominators, I can write my final answer as either root 2 plus root 6 over 4. And that is a perfectly acceptable final answer for me. But you might see the book factor out a root 2 in the numerator. So root 2 times the quantity 1 plus root 3 over 4 is also acceptable. And here we are at example 1. We're going to find the exact value of the sine of pi over 12. Again, this is not an angle that we've been able to do an exact value in the past, but if I could represent pi over 12 as a sum or a difference of angles that I already know the exact value of, then I can apply the sum and difference formula to find the exact value. So the beauty of pi over 12 is we've sectioned off our unit circle in twelfths. So you just need to find any combination of something over 12 minus something over 12, that gives you pi over 12. I'm going to stick to first quadrant angles because life is good. And I'm going to represent sine of pi over 12 as 4 pi over 12 minus 3 pi over 12. So again, I say to myself, self, how does the sum and difference formula for the sine of a sum or difference work? Well, the sine is sine, cosine, cosine, sine. Then I alternate the angles. So 4 pi over 12, then 3 pi over 12, then 4 pi over 12, then 3 pi over 12. And the order makes a difference this time because 3 pi over 12 minus 4 pi over 12 is a negative pi over 12. So it matters with the difference. Differences are not commutative. Next, I use the same sign. So since this was a difference, the formula also contains a difference. Now, for those of you that it's bugging you that I'm in 12ths, I could reduce each of those. So 4 pi over 12 reduces to pi over 3, and the 3 pi over 12 reduces to pi over 4. And now my next step is just to evaluate each of those trig functions. So the sine of pi over 3 is root 3 over 2. The cosine of pi over 4 is root 2 over 2. And because I'm keeping all my angles in the first quadrant, and again, not every problem is going to allow you to do that, I don't have to worry about if any of these values are positive or negative because everything is positive in the first quadrant. Then I'm going to subtract the cosine of pi over 3, which is a half, and the sine of pi over 4, which is root 2 over 2. Next, I'm going to use my please excuse my dear Aunt Sally rules, and I need to do the products before I do the difference. So root 3 over 2 times root 2 over 2 is root 6 over 2. Then I'm going to subtract root 6 over 4. Then I'm going to subtract off root 2 over 4, and since they are a common denominator, I have root 6 minus root 2 over 4, and again, I can factor out the root 2, multiply it by the quantity root 3 minus 1 over 4, and either of those would be acceptable final answers. And here we are at example 2, where we have to find the exact value of the cosine of u minus v given some information about angle u and about angle v. So let's just start with the cosine of u minus v. If I think about my sum and difference rules, sine, cosine, cosine, sine. Okay, cosine is cosine, cosine, sine, sine. So cosine, cosine, sine, sine. And when I'm doing a sum or difference of cosine formulas, you have an opposite SIGN sign. So I'm going to add their products because I'm subtracting the angles. Now, the only information I know so far is I know that the cosine of v is negative 3/5 and the sine of u is 5/13. What I don't know is the cosine of u and the sine of v, and I have to figure that out. So how do I figure that out? Well, let's take a look and make a triangle. Okay? If I put a triangle in the second quadrant, and I'm putting that in the second quadrant because they gave me information that angle u is an angle that is between pi over 2 and pi, or between 90 degrees and 180, so it's in the second quadrant. Since the sine is the y-coordinate over the radius, I've marked my triangle appropriately. So what I do next is Pythagorean theorem, and I know that x is 12, but you have to be careful. Since we're in the second quadrant, x isn't just regular 12, it is negative 12. So that means that my cosine of u is going to be negative 12/13. I'm going to apply the same process for angle v. I am given some information that v is located in the second quadrant as well. It's between pi over 2 and pi, or so between 90 and 180. And cosine is defined as x over r. And my radius is always positive because that is a distance. So the negative is going to apply to my x value of negative 3. Now, I didn't write out the work for this one because hopefully you remember, just like 5, 12, 13, which is a Pythagorean triple, 3, 4, 5 is a Pythagorean triple. So because I'm in the second quadrant and y values are positive, it means my y value is 4. Therefore, the sine of v would be 4/5. So I'm going to put those values back in. Okay, so I originally knew that the cosine of v was negative 3/5, and I originally knew that the sine of u is 5/13. But then when I did my triangle work, I now know that the cosine of u is negative 12/13, and the sine of v is 4/5. And now I simply use my please excuse my dear Aunt Sally rules, and I multiply negative 12/13 times negative 3/5, which gives me 36/65. And I multiply 5 times 4, and then 13 times 5 to give me 20/65. And I add those together to get my final answer of 56/65. And we are at example trace. And believe it or not, this is one of the simplest problems. It should take you less than 30 seconds in your homework, and yet is one of the most missed questions kids will get, because this is just a problem that takes the sum and difference formula and goes backwards. They want you to write the expression as the sine, cosine, or tangent of each angle. So the first thing you have to identify is, well, I see sine, cosine, cosine, sine. Okay. So hopefully that reminds you that this is the pattern for the sum and difference of sines of angles. Then you need to remember, well, I'm adding the products of each of those sides, so the sine, S-I-G-N sine, is going to stay the same. So I can condense this expression to the sine of 110 plus 80, because 110 was the first angle and 80 was the second. And then all I have to do is add 110 degrees and 80 degrees to get my final answer of the sine of 190 degrees. And we have arrived at example 4. I believe that this example, of all the ones that I'll present in this video, is not the one that is most intuitive. When you're being asked to write the trigonometric expression as an algebraic expression, you might be thinking, what the function map? Okay, so we've got the cosine of the arc cosine of x minus the arc sine of x. You're taking the cosine of a difference. So you need to remind yourself that I have to apply the sum and the difference formulas. So when I'm doing cosine, you might do the chant in your head, sine, cosine, cosine, sine. Okay. Cosine, cosine, sine, sine. Cosine, cosine, sine, sine. We don't have numeric values for the first angle and the second angle. We have expressions. We have arc cosine of x, arc sine of x, and then arc cosine of x, arc sine of x. Because this is a sum and difference of a cosine, I have opposite signs. Now, you might be looking at this as gibberish, and so did I the first time I did this. But if you notice, when you take the cosine of the arc cosine of x, those are inverses of each other. So that is just going to simplify to x. On the right side, you should see the sine of the arc sine of x. That is also going to cancel, since they're inverses, and simplify to x. What I don't know to put in is, what is the cosine of the arc sine of x and what is the sine of the arc cosine of x. And this is not as intuitive. So we're going to talk very general. We're not going to be talking in specific numeric values, so follow along. All right, here's what we're going to do. I'm going to do some substitution. You're going to see a lot of this throughout this school year, where it's just going to allow us to think of things differently. So I want to focus on this left side. We're going to let u be the arc cosine of x. So in doing so, the cosine of u, if I take a cosine of each side, the cosine of u equals the cosine of the arc cosine of x. So all I did is took that equation and I applied cosine to both sides. The cosine of the arc cosine of x will undo each other and simplify to x. So then I drew a general right triangle. If the cosine of u equals x, you can also think of it as x over 1. Then the adjacent side to u is x, and the hypotenuse is 1. What I can do next is Pythagorean theorem using general cases. So I can do x squared plus y squared equals 1. I am solving for y. So y squared is equal to 1 minus x squared when I subtract x squared from both sides. And then when I take the square root of both sides, I get that y is equal to root 1 minus x squared. I don't have to worry about the negative part of that because we're talking about a distance. Okay, so if you understand where we're getting those values, see if the following makes sense. The sine of u would be opposite over the hypotenuse. So the opposite is the square root of 1 minus x squared over 1, which is the radius. But we defined u at the very beginning to be the arc cosine of x. So if I substitute that in for u, I get that the sine of the arc cosine of x equals the square root of 1 minus x squared. And we will substitute that value into the difference of that cosine expression we had on the previous slide. Now let's look at the right-hand side where we talk about v is equal to the arc sine of x. It's going to be an extremely similar conversation. If I apply a sine to both sides, the sine of v is equal to sine of the arc sine of x. The sine of the arc sine of x will simplify to x. And now I can draw a general right triangle where opposite of v is x and my hypotenuse is 1. The Pythagorean theorem work is exactly the same as I did before. So the other side of the triangle is also going to yield 1 minus x squared. Therefore, if I look at the adjacent over hypotenuse, the cosine of b is the adjacent side of the radical 1 minus x squared over 1. And again, we defined v to be the arc sine of x. So if I substitute arc sine of x in for v, I get that the cosine of the arc sine of x is equal to root 1 minus x squared. So let's go back. I have the cosine of the arc cosine of x times the cosine of the arc sine of x plus sine arc cosine of x sine arc sine of x. What I was able to do is remind myself that the cosine of the arc sine of x is x, the sine of the arc sine of x is x, but I was able to substitute in the sine of the arc cosine of x equals the square root of 1 minus x squared, and then substitute that same expression in for the sine of the arc cosine of x. Next, I could write it more simply as x root 1 minus x squared plus x root 1 minus x squared, so that my final answer is 2x when I combine like terms, the square root of 1 minus x squared. Whew! After example 4, you'll like example 5. This one is pretty easy and to the point. We need to verify the identity. So I'm looking at the sine of 3 pi minus x equals sine x. And I notice, hopefully, wow, I've got a sine of a difference of two angles. So I need to apply the sum and the difference formula. So I'm going to do sine, cosine, cosine, sine. I'm going to alternate my angles. And the SIGN sign, since I had a difference, stays the same since it's sine. Next, I'm going to evaluate the sine of 3 pi and the cosine of 3 pi because that was a concrete angle and I'm able to find their exact values. So the sine of 3 pi, which is going to be the same as the sine of pi, is 0. The cosine of 3 pi is negative 1. And the next step is to just do some simple algebra. 0 times the cosine of x is 0, leaving me with subtracting a negative 1 times the sine of x. And last but not least, a negative becomes a positive, and I yield the sine of x, and I have made the left-hand side look like the right. We did it. We made it to the last example. Welcome to example 6. We're going to find the solutions of the equation in the interval from 0 to 2 pi. So we don't need to find the general solution, just all of the solutions within one revolution. We're going to use a graphing calculator to verify our results. So I have the cosine of x plus pi over 4 minus the cosine of x minus pi over 4 equals 1. All right, so fantastic. We have a sum and a difference of angles, and we're taking the cosine of them. So really, this equation isn't awful. We have to apply the sum and the difference of a cosine twice. So let's deal first with just the cosine of x plus pi over 4. So By now, we remember that the pattern for cosine is cosine, cosine, sine, sine. Because I am adding the angles, I am going to take its opposite sign and then alternate my angles. So cosine x cosine pi over 4 minus sine x sine of pi over 4 is how the cosine of x plus pi over 4 expands. Next, I have to subtract, and notice how I've done the next pattern all in parentheses to make sure you have the proper signs, SIGN signs. So again, I've got a difference of angles, and I need to take the cosine of that difference of angles. So I'm going to use cosine, cosine, sine, sine. Because I'm taking a difference of the angles, then I take an opposite sign and add the products of the cosines and the sines. And then I alternate my angles, x pi over 4, x pi over 4. In the next step, I am going to distribute the negative. And cosine x cosine pi over 4 becomes negative, but then so does sine x sine pi over 4. So what happens is the cosine x, the cosine pi over 4 terms will cancel, yielding me, when I combine like terms, with negative 2 sine x sine of pi over 4 equals 1. What should I do here? Well, sine x is a general case, but the sine of pi over 4 is a concrete angle, and I can evaluate that. So in the next step, I'm going to evaluate the sine of pi over 4, which is root 2 over 2. With some simple algebra, the 2's are going to cancel. And will yield a negative root 2 sine of x equals 1. In order to isolate sine of x, I'm going to divide both sides by root 2, negative root 2. So the sine of x is equal to negative 1 over root 2. For those of you that prefer it rationalized, would be negative root 2 over 2. Then I need to go to my unit circle, and I need to find all the places where I have a y value that is negative root 2 over 2, and that is going to occur in the third quadrant at 5 pi over 4 and in the fourth quadrant at 7 pi over 4. Let's verify our answers. Okay, so I went ahead and graphed this on a graphing calculator. If you notice, the blue is cosine x plus pi over 4 minus the cosine of x minus pi over 4, and the red is 1. So where those two equal, their intersection points, is the answer. Now what the calculator will do is generate a decimal approximation. So what I've done in the other screen is shown you that our answer of 5 pi over 4 radians is equivalent to 3.92 or 3.93 when rounded as a decimal form, and that 7 pi over 4 would be equivalent to 5.5 in rounded decimal form. So our graph, our algebra, all makes sense. So in class tomorrow, you will have time to work on learning opportunity number 1, which is page 372, 1 to 29 odd, 35 to 49 odd, 55, 57, and 61. Look forward to talking with you tomorrow.